Okay, in this video, we're going to try to summarize the trends in the position and velocity versus time graphs and the relationships between all of these variables that we've been talking about. So we know from the last chapter that velocity is the rate at which an object's position changes. It's displacement over time. So that means because rate of change with respect to time, that's slope. So then what we're really looking at when we look at a velocity versus time graph is how the slope of the position time graph is changing as time goes by. We're basically graphing the slope of the position time graph when we make a velocity time graph. Okay? And then when we talk about acceleration, we're doing that all over again. We're finding the slope of the velocity time graph because we're wanting to know how fast is this thing changing velocity. So we're graphing the slope of the velocity time graph. If we make an acceleration versus time graph, we don't do that very often, but you can do that. In chapter 3, most of the time we are just going to focus on acceleration being a number. Is it a positive number, like positive 3 meters per second squared? Or is it a negative number, like negative 10 meters per second squared? Okay. So I thought this table hopefully will help you kind of get all the situations and relationships put into your head. So, first and most simple situation, okay, would be when the position versus time graph is just a flat line, which would be the situation when the thing is not moving, it's just standing still. So, in that case, that thing is not moving, therefore, it has a velocity of 0 as time goes by. So you would just draw a flat line, okay, because the slope of a horizontal line is 0. And if that's not changing as time goes by, you would just draw another horizontal line, but this time at 0 meters per second, or whatever your units would be. Okay, and then if this is a flat line as well, the slope of that is going to be 0 as well. And we just said it's standing still, so it's not moving. Okay, so if you want to pause the video to write that down. Then, okay, another situation we had in the last chapter was what if the position versus time graph is some kind of diagonal line? It could have a positive slope or a negative slope. So in that situation, that's when the velocity time graph just makes a flat line, but it's something not on 0 meters per second. Okay, so I'm going to draw, let me see if I can draw in here with my pen. So that means like the position time graph might look like a diagonal line, and then the velocity time graph is going to look like a flat line, because if this one has a slope of, let's say, 2, then this one is going to have a velocity. This is a position. Okay, then this one is going to have a constant velocity at that level, right? If it had a velocity of like -1, right? Then you would have instead something down here at -1. Okay, but then when you do the slope of this graph, okay, to get the acceleration, well, it's not accelerating. It's not changing velocity, so it just has 0 acceleration still. It's moving in a constant velocity. Okay. Let me pause and erase that. Let's take this chapter as an example though now. So what happens if you have something more complicated? Okay. For instance, the object is speeding up. That's what they're giving us here in this scenario. That's talking about speed, so we have to be careful. That's not velocity. But the easier way to describe this is just to draw these graphs. And you can see, okay, in the velocity versus time graph, that the velocity is going away from 0 because we know that 0 is at the x-axis, right? So I would have 0 meters per second here. At the middle, right? So that represents when things are stopped. And so anytime the graph goes away from 0, then I know that object is speeding up. On the position time graph, I know it's speeding up whenever I see the graph getting steeper. So I can see, for instance, that at the beginning of this red graph, let me choose a different color like green, let's say. So when I see at the beginning of the graph, if I kind of check the slope at the beginning, it's almost flat. But then if I check the slope at the end, it's very steep. And steepness, remember, is talking about speed on a position time graph. Same here. If I had like if I check the slope at the beginning, it's not very steep, pretty slow, that means. But then at the end, oops, it's very steep right there. So that means fast. Even though it's a negative slope, don't let that bother you, right? Steep means fast. So then those are two examples of how it would look for a position versus time graph for something speeding up. And then when we talk about acceleration, the way to remember this is whenever the sign of the acceleration matches the sign of the velocity, you will know it's speeding up. So for instance, either both acceleration and velocity are positive, or both acceleration and velocity are negative. That's speeding up. Okay. And then last situation is when the object is slowing down. Okay, we can tell that. Let's look at the velocity time graph. It's coming down to the x-axis as time goes by. It's approaching the x-axis in some way. So it's getting closer to 0. If we look at the position time graph, we should see it leveling off. So it's not as steep as it was at the beginning. Here we see it's nice and steep at the beginning, not very steep at the end. Very steep at the beginning here, not very steep at the end as time goes by. And then when something's slowing down, the way you can tell if you just have numbers is that the acceleration and the velocity have a mismatch of signs. They have opposite signs. One is positive, the other is negative. Okay? All right.